Okay, so we'll have the second part, the second lecture by Pietro. He will continue to tell us about the black hole thermodynamics.
Thank you. Thanks. Okay, so I'll start with a short review of yesterday, and then, well, not really, but, and then we'll move to black hole thermodynamics. Actually, I will not do black holes. I will do flat space thermodynamics, but you can map flat space to a black hole, as we will see at the very end. And then I will tell you how you can do the Hawking, how you could prove the Hawking effect. But I will not have the time to actually go through the details of the computation, which is quite involved. Okay, so the conclusion of the lecture yesterday was that if you have a bifurcate Killing horizon, then it has some geometrical properties, it has some geometrical quantities that define it, such as a surface gravity, which depends on the normalization of the vector. This will be important, as we will see later. But the main idea is that there are properties that really look like thermodynamical, the laws of thermodynamics. So the reason the paper that I mentioned yesterday, the Bardeen-Carter-Hawking paper on black hole mechanics, was written was in response to a suggestion by a student in Princeton called Bekenstein, who thought, after a suggestion from his supervisor, Wheeler, about the following problem. Some of the theorems that I have not mentioned, but characterize black holes in asymptotically flat space in 4 dimensions, is that they are the endpoint of any gravitational collapse. And then if you start with a star of some that is described by a certain equation of state, certainly its content, its mass, its flares and stuff, then it will at some point live its life, and at some point, if it's sufficiently big, it will explode, and it will end up in a collapse that you expect after some temporary fluctuations to end in a stationary state, so in a state that doesn't depend on time, formally from the geometric viewpoint, such that you have a Killing vector that is time-like. This state is, and there is a theorem that provided some assumption, is unique, in the sense that there is a unique solution to the Einstein's equation with a black hole in it, so the black hole spacetime, that is and this solution is identified only by 3 parameters in 4D. So this statement goes under the name of uniqueness theorem, and in 4D asymptotically flat space, there exists a unique solution with parameters M, Q, J, which are the same ADM charges that we saw yesterday, so the ADM energy or mass, the electric charge, and the ADM angular momentum. This solution is called the Kerr-Newman, after the people who wrote it. Aside, interestingly, this theorem doesn't apply if you go to higher dimension. So you can violate this theorem in different dimensions. You can either go to 5 dimension and higher, where there are solutions that have a black hole horizon, but also solutions that have more intricate topologies as their horizon, such as black rings or so on. But you can also violate it still in 4 dimensions if you go to asymptotically ADS spaces, where you don't have a uniqueness theorem anymore. You can have the ADS Kerr-Newman solution, but you can also have different solutions if you remove the angular momentum. Okay, that being said, we start with this uniqueness theorem. So you have a gravitational collapse, it does something, it does some faff, and then it ends up in the Kerr-Newman. Now suppose I throw some gas in it, or a person in it. So after a while, it will settle down to another Kerr-Newman solution with a different mass and a different angular momentum, but it will have forgotten all the information about this gas that was there, right? Or the thing I throw in. We have a lot more entropy than the thing that is just defined by a mass and angular momentum, right? You would need to say that I'm wearing a red t-shirt, I'm wearing some jeans. All of this is irrelevant for the gravitational collapse. What the star was made of is all irrelevant. So this seems to contradict the second law of thermodynamics, the real second law of thermodynamics, because I can effectively lower the entropy of the universe. I can dive in a black hole, and then you will never know whether I was wearing a red t-shirt or a blue t-shirt. So that's a loss of entropy in a sense. So Bekenstein thought it's impossible. Therefore, there must be a notion of entropy associated with the black hole, with the idea of a black hole. And he had a revolutionary, this was already a revolutionary idea, but then he had a more concrete idea, because you can just say these words, but then he had a concrete prescription to solve this problem. He knew that the year before his paper, Hawking had proved what I called yesterday the second law of black hole thermodynamics, mechanics, which at the time was just called the area theorem. That is that if you have a strongly predictable asymptotically flat spacetime, black hole, then the area of the event horizon for any sufficiently continuous evolution will increase. So he thought, well, clearly, this is a revolutionary idea, the entropy of the black hole is proportional to the event horizon, to the area of the event horizon. And this makes sense because it's consistent with the area theorem that we had earlier. It's also consistent with the picture that he knew from information theory. In information theory, which is how we think of entropy right now, is the notion of entropy is a notion about the lack of information about a system, right? So we define it depending on the rho, some density matrix of your system. So in this sense, given a mass, a charge, and an angular momentum that defines the black hole, the entropy of the black hole is the notion of how many states are in the black hole and that we don't know the details of. This is not how we phrased it, but that's the idea. It's a measure of the equivalence class, of the size of the equivalence class of black holes that have these parameters. So it cannot be a classical idea, because the classical, so long as classical mechanics is involved, this solution is unique. So you need to go beyond classical mechanics, right? Which means that you need to introduce an H-bar in the system, because you need to introduce quantum mechanics. He was very happy that this made sense, because it's easy, just write it down. With only the velocity of light and the Newton's gravitational constant, you cannot make this entropy dimensionless. Remember that the Boltzmann constant is 1, or just put it in front, right? So you want a dimensionless quantity, but you cannot make one just using C and G, because G contains a mass. So you need something with a mass, and H bar does contain a mass. So there is a way of writing the entropy in this way. You just multiply the area of the event horizon by this factor. This factor has the same dimension as an area, as area to the -1. In fact, it's sometimes, this is also the Planck length to -2, so it's the area of a Planck bit. And you notice that this entropy diverges as H bar goes to 0, right? So it becomes finite only when you consider H bar effects. So this is all fine, and he says, this is what we're gonna have. This is the entropy of a black hole. That's kind of the end of his paper, in a sense. For eta? Ah, did he? What, I don't remember. Oh, okay, order 1, okay. Oh, okay. Ah, no, that's true. Yeah, now I remember. Yeah. But so then Hawking and Hawking's group, who were in Les Houches, as I mentioned yesterday, for some summer school, realized that this was the case, read this paper and thought this is absurd, because if you have a thermodynamical object with an entropy, then it must radiate. So, but a black hole cannot radiate, as we said yesterday many times. So they wrote this paper with the 4 laws of black hole mechanics that really reads like, should be the laws of thermodynamics. And then at the end, they just say, it's impossible. This doesn't make any sense because a black hole is a perfect absorber. In particular, you'll remember from yesterday that one of the laws of black hole mechanics, the first one, said that in GR, this is true. Omega dj. So this is really like the first law of thermodynamics for a system with energy E plus all the sum of all the chemical potentials times the variation of the conserved charge that is associated to that is conjugate to the term. So it really looks like this, and you can associate the area to the entropy, provided you say that the black hole has also a temperature. Now I'd like to keep the factors correct. So 8 pi eta. So you'll notice that this temperature makes everything consistent. So if you associate the temperature, if you associate this temperature to a black hole, then the 0th law of black hole mechanics really tells you that the temperature on the body is constant, just like the 0th law of thermodynamics. The 3rd law says that, we said yesterday that you cannot have an evolution from subextremal to extremal, where extremal and subextremal are defined in terms of the fact whether the surface gravity of the horizon is 0 or non-zero. And it's also in this sense. But you'll notice that there's an h bar in the numerator. So if we just do classical physics, where the h bar is equal to 0, then the temperature must be 0, which is consistent with our classical statement that black holes are just perfect absorbers. So in order to show that this effect actually exists, you need to consider quantum mechanics in the black hole, quantum field theory, in the black hole background, and show that that you see an emission from the black hole. In particular, Hawking did the computation, showed that this is the case, and therefore set eta is equal to 1/4, which is consistent with the normalization that I used yesterday for the world's entropy. Yes. So once we show this, then we can really say that a black hole is a thermal object from the quantum mechanical viewpoint. Okay? This is what we're going to do now. Questions about this? Yes?
So these charges, what sort of charges? They are rotating
Here? Yeah. Oh, yeah. Ah, yeah, that's the same. Yeah, so in asymptotically flat, there are at least 2 ways of defining the charges of a spacetime associated to a spacetime. One is in another theorem type argument. So you have a killing vector, so you have an isometry of your system, and then you can construct a current that is conserved using this killing vector that follows from the fact that the killing vector, the derivative of the killing vector is antisymmetric, so it's a form, and then you can consider it star dxc, and that is conserved. So you can integrate that on an asymptotic sphere. So star dxc, if xc is a killing vector, this is a 2 form, this is a 4 minus 2 is also a 2 form, and you can integrate it on S2, At infinity, this will give you a charge, and that is conserved in the sense that it doesn't depend on the way you take the S2 because of Stokes' theorem. And this is one way. This is called Komar. Or, after the person who came up with this way, or you can use the framework that I was using yesterday, which is called ADM, after Arnovitz, Deser, Misner, and which is by comparison with the asymptotically flat space. So the mass is whatever appears as the leading order in the Newton potential, in the Newtonian approximation to GTT or something, and the angular momentum is whatever appears in the cross terms between time and the Cartesian coordinates in the opposite plane, in the transverse plane. So yeah, it's a sort of another theorem.
When we do, for instance, most results relating the energy variation to the energy weighting of the parameters, this really contains all the charges linked to the black hole itself, like mass, charge.
So here we are here the space-time that I'm discussing here is a space-time that only contains a black hole. There's a black hole, nothing.
Well, now in order to derive the temperature, you have to extend beyond, right? You have to add some field.
Yeah, so I take a black hole and then I fix it. So I'm doing quantum field theory on a fixed background. So I'm considering what is the excitations of the field around this background without ignoring the back reaction on the background. So in that sense, it doesn't back react, so it doesn't change this MQJ.
If I am willing to consider some exotic field that has some internal charge or internal symmetry or something like that.
Oh yeah, if you consider a fermion and so on, you will find the same result, but that's because the spectrum, the Planck spectrum, has a form for a boson, has a form for a fermion, and has a form for a rotating body. So if the black hole is rotating, then there will be a preferred direction of emission. But this you already knew, in the sense that if I give you a star, or if I give you something that is warm, like a cup of coffee, and you rotate the cup of coffee, then you'll receive a thermal distribution, you measure a thermal distribution that depends on the direction of rotation. But these are all properties of the black hole. Other questions? Okay, good. So, as I said, I will not actually derive this result. I will derive something related to this. So, let me first, so this was the introduction. Let me tell you about QFT in curved space. So, I remind you of your QFT course, if you've had one. When you do QFT in Lorentz symmetric spacetime, so like in flat space, what you do is that you take the Klein-Gordon equation and then you expand the field on a basis of plane wave solutions to this Klein-Gordon equation, in the sense that I define of modes that are labeled by some p, that is a vector in d-1 dimensions, that has the property that the eigenvalue with respect to this operator, which is I times the derivative along time, is omega is positive. This is called the frequency. I'm just formalizing things that when you first opened Peskin were given for granted. You just expand the field, you do a Fourier transform. That's the less fancy way of saying this. But the point is that you associate the positive frequency, choosing the basis to be of positive frequency, guarantees the possibility of constructing an inner product on this space, on the space of complex solutions to the Klein-Gordon equation that is Hermitian and is positive definite too. So you can really construct a Hilbert space on this. So in particular, when we expand phi on this basis of UP, so integrate on P, say that we are in 4 dimension. Where do I put this? Okay. And then I call the coefficient, then I do the quantization. So I take phi into an operator, and I call the coefficients annihilation and creation operators. Because the Klein-Gordon inner product that you put on the space of positive frequency solutions to the Klein-Gordon equation, together with the canonical commutation relation that you impose on phi and its canonical conjugate. So you impose that this is some delta and that phi here I'm being schematic, but that's the idea, right? You take the commutation relation, you promote this, you look at what are the commutation relation on A and H dagger, and the result is that A and H dagger and A dagger satisfy the canonical commutation relations for the creation and annihilation operators. Therefore, since you have a positive definite operator, positive definite inner product here, you can construct a Hilbert space in the same way as you do for the harmonic oscillator. You define a vacuum for all p that is annihilated by everything. Then you construct the one particle states, the n particle states by successive iteration of A dagger, and then you symmetrize everything in order to take into account the indistinguishability of particles, and then you say that the Hilbert space is formally, perhaps you have heard these words, is the symmetrized Fock space constructed from the harmonic oscillator. So the Fock space is the tensor product of all these that contains all the n particle states, and then you symmetrize to take into account indistinguishability of these particles. Okay, so far so good. I'm sorry for those of you who have never seen this, if you have not taken a graduate course on QFT, but perhaps from quantum mechanics you know the harmonic oscillator. This is just a fancier harmonic oscillator. What's the problem with doing this in curved space? That generically, there is no notion of a time-like Killing vector that I can use to define the positive frequency solutions. And therefore, there is no notion of this entire construction. So on a generic curved background, even if you assume that is causally well behaved, so that is technically globally hyperbolic, that's the fancy words we use, there is no notion of a vacuum. Which means that there is no notion of a particle. So you may say, well, that's wrong. And but then you should remember that really we're doing field theory rather than particle theory. So I think that This is what the course on operator algebra is about. I'm sorry, but it's in Portuguese, so it's beyond my abilities. But there is a way of doing quantum field theory on a curved background without resorting to the notion of particle and vacuum, which is the proper way of doing quantum field theory on a curved background. This is in analogy, if you think about, without talking about Hilbert spaces, basically. This is in analogy with how we are taught GR, right? We first learn special relativity, and it makes heavy use of the coordinates, because there is a special choice of coordinates, there is Lorentz invariant, and so on. But then we learn GR, and we forget about coordinates. There shouldn't be no coordinates mentioned. It's all diffeomorphism invariant. In the same sense, there is a way of doing quantum field theory that doesn't involve a Hilbert space construction, that focuses on invariant statements, such as states and the algebra of operators. With this notion, in this way of doing quantum field theory, which is sometimes called the algebraic approach to QFT, the central object is the algebra of observables that is associated to any subset of your curved background. And then you define a state as a functional on this space on this algebra of observables, in the sense that you define the state by looking at what is the value that all the possible observables take on that state. So a state is a map from the algebra to complex or real, depending whether it's depending on the choice of field that you're using. So this is the proper way of doing quantum field theory on a curved background. I will not do that. This is beyond my abilities as a mathematician. This involves a lot of functional analysis to do it properly, and so I'm not going to do it right now. I'm going to just use one property of a state that identifies it doesn't really identify the state from the two-point function. From the two-point function, we define the KMS state, which has the property that is a thermal state. It's the state that an observer who perceives a temperature as. These are Kubo, Martin, Schwinger. And I should also mention, just for fun, two things about the algebraic approach. So, in a sense, this was bound to happen, because there is a theorem in functional analysis that says, this is the Stone-von-Neumann theorem, that says that there is only a unique representation of the canonical commutation relation in a finite dimensional system. But if you are in infinite dimensions, such as in QFT, there is no such thing. There is no unique representation, modulo unitarity. The only reason we can do QFT in this way, in flat space, is because there is Lorentz symmetry that helps you pick out a particular representation. Otherwise, there is a way of constructing a Hilbert space, if you are really keen on the Hilbert space, from this approach. It's called the Gelfand N and Segal N. Neumann? Sorry? Neumann. Okay, Neumann condition. Okay. So I will now move to the KMS condition. If there are questions, stop me at any time. Don't wait for. Yes. I'm not sure I followed the question. Okay, but the idea of the algebraic approach is that you can prove rigorously that, for instance, the Rindler observer, for any interacting QFT, if whatever the interacting QFT you may choose, and this is the power of algebraic QFT because it's any algebra of observables that you may want, will perceive a temperature in the sense that if you go on the word line of the Rindler observer, then you will always be in the KMS state associated with that temperature, which is the way we define a thermal state, which is what I'm going to do now. Okay? So let me tell you about thermal states. So the other thing that is different when we want to study the Hawking effect compared to the canonical class on QFT is that in canonical classes in QFT we look at pure states, which are uniquely defined from their quantum numbers, from the conserved charges. Instead, when we do QFT in presence of a temperature, we should really be talking about mixed states that are defined by their density matrices. So let's consider a simple system where you label the pure states by the eigenvalue of the Hamiltonian, the energy, which is the only number that is allowed to vary. So I'm in the canonical ensemble at a fixed temperature T. The probability that you are in a pure state with energy E is the Boltzmann weight, where Z is just a normalization factor that guarantees that the probability sum to 1. The expectation value of an observable O in the mixed state, where beta from now on is 1 over T. Sorry, I didn't say it here. K is 1, remember? So this I'm sure you've seen. It's just the sum over all is the weighted sum over the webs, not the webs, the value of the observable measured on the state. So it's the trace of O divided by Z. Okay, so this is the value of the observable, this is the expected value of the observable on the mixed state. Now, consider an observable. For any observable, I can do the time evolution using the Heisenberg picture. So I can create a one parameter group of observables that is labeled by the value of the time. And I can define some correlators of observables at different time. A and B are two observables. These are by construction. And this I will call G plus beta T A B. Sorry. And then I will also consider, which is just the different order, and these are called G minus. Okay? More properly, I should define them on compact spatial manifold because I need to make sure that the trace is bounded and it's well defined, blah, blah. Imagine that I've done that. Okay, so far so good. Notice that these two correlators are just a commutator. The difference of the two is the commutator. That's why they will be relevant now. Okay, so now I extend these to the complex T-plane where z is a coordinate. So z is t plus ite, where both of these are real. And t is equal to 0 corresponds to the real z part, which is where these are defined by physics. So now I'm going into mathematical physics, really, because that's the title of the school, in the sense that there's no physics here. Okay? I will do something bad from the pedagogical viewpoint. I'll just do this. So this is the analytic continuation of these observables. Now, there's a bunch of properties of these that I can just derive from the definition. So consider, for instance, G plus beta, ZAB. Using cyclicity of the trace and their definition using the Heisenberg picture, this is Z to the minus 1. Sorry, H, B. And similarly, it's B. So once I've written these, you'll see that in order to have a real part that is negative in this exponent, so that the trace has a hope of converging, then the presence of beta restricts the holomorphicity of these two functions. So in fact, G plus beta is holomorphic in this strip, and G minus beta it's holomorphic on this strip. And they agree with their t value once I take imaginary of z to 0. There is another property that follows from the cyclicity of the trace, which is that I can actually turn one into the other, provided I change the argument. Cyclicity is Kukros. If then G plus so this is kind of a periodicity modulo the fact that I've switched the order of the observables, right? So this I can also rewrite using that construction. It's very evocative if I just write it using T. This formula is the KMS condition. It allows a lot of fun because thanks to this periodicity and the fact that I am studying a QFT that is relativistic, so the fact that the commutator in real times must vanish for space-like separations of the two points. So imagine that I have two operators. Then if t is smaller than x minus y, say, I take two operators at the same time but at different points. Then if the separation between the two operators is larger than the time, then the commutator vanishes. So this is a z-plane where t is the real component. So this is non-zero only if this holds. And here, on this particular interval, because the commutator vanishes, G plus is equal to G minus. And then at imaginary Z equals to beta, I will have either G minus, G plus beta, and then here I will also have G plus beta, because it doesn't need Z, I can extend them indefinitely, right? Because using this periodicity. So I can construct, and here there's a G minus, this is beta, beta, and here I have the same analytic structure. I have a pole, and I have something that I don't care about. Now, if you use some complex analysis theorem, just take an integral along a contour and split it along the real line, then you can show that actually G plus and G minus are one the analytic continuation of the other, since they agree on this strip. So I can construct, the final result is that I can construct an analytic function, well, a function that is analytic modulo these lines here, where I don't know what happens and I don't care. Such that is G minus in this strip. So if 0 less than imaginary of Z, less than beta, and G beta is G plus minus beta. So this is defined in this way. They agree on this point, so it's an analytic function that is well defined everywhere. And it's also periodic thanks to the KMS condition. So every time Z goes to Z plus imaginary of Z goes to imaginary of Z plus beta, or plus any multiple of beta, then I simply switch from G minus to G plus, and so on. Okay? In the way that I constructed here. Now, this I all derived by assuming that I was in a mixed state. Now I think about it like an algebraic quantum field theorist. So rather than starting from the states, I start from what is the property of the two-point function, and I use this to define the state, right? Because remember that that's the idea of the algebraic quantum field theory. The state is a function from the observables to the complex numbers. So I say that a thermal state at a temperature T is defined by the fact that its the correlation functions measured on that state have a periodicity in imaginary time, so formally they satisfy the KMS condition with a periodicity beta that is the inverse of the temperature. Okay? That was a weird wind, but I know that there will be questions. Just ask the first one that comes to mind. Then we'll see what I can improve of this. That's, you're spot on. Exactly. So, why is this? Yes, so this is precisely a Wick rotation. So what I've done here, take beta to infinity. So these lines, the periodicity just goes to infinity. There is no periodicity, right? So I have a pure state. I have temperature 0. These two are the poles of my propagator. And precisely what I'm doing is the Wick rotation. I'm defining a function via an extension that is precisely the Wick rotation. So on Z is equal to 0, so at this point, I have T is equal to minus ITE, and I can relate the two objects. The other great property of this, which is the property of the Wick rotation, is the fact that the Klein-Gordon equation here, it's an hyperbolic partial differential equation, which means that its Green's function are non-unique, which you know because you've been taught that there is a Feynman propagator, a retarded time propagator, an advanced time propagator, depending on the way I go around the poles. But when I do the Wick rotation and I go on the real line, well, on the imaginary line, on this line, there are no more poles. And then the Green's function is unique. So, what we are going to do next, thank you for the segue into the next chapter. So, what we're going to do now is consider a particular setup in gravity, but actually in flat space, and show that if you quantize a massless scalar field on that particular setup, which is the Rindler observer, you'll find that you can extend the two-point function to an analytic function everywhere on the plane modulo these strips that is unique because its restriction on the imaginary line is the Green's function for the Wick-rotated Klein-Gordon operator, which has a unique Green's function. And moreover, it has the property, this function that we're going to define now, it has the property that is periodic, so it satisfies the KMS condition, with a periodicity that is fixed by the acceleration of the Rindler observer. Then we will conclude, basically I've already concluded, that the Rindler observer is in a state at a temperature fixed by its acceleration, by her acceleration. Okay.
I'm used to when you do this properties, you apply that your exact direction and it will become an S1. So it will happen there.
Yes. Yes. Well, I can just put down the notes, you know. You can just give the lecture like this. Yes. So what does this mean, this periodicity? Just look at, rather than looking at T, so here I wrote it in this way that is particularly, you know, evocative, but really this is the proper way of looking at it. So now, write Z in this way, and here I have T plus I, T plus beta. But this means that effectively, the geometry over which I'm considering the field theory, this requires a sleigh of n that I will tell you later about, has become periodic because I can identify TE with TE plus beta, so it's S1. Okay, sorry, that turned out to be a conversation, but I hope. Other questions? Okay, now I will basically put some numbers into what I just said in the past 5 minutes. So, we consider a massless scalar field on flat space. This will not be a massless, a massive, do whatever you prefer. Let's make it massive so that we don't have IR divergences. We define the two-point function with the plus in the same way as above. This stands for phi of xi, phi of x, phi of y. These are two different operators, right? A and B, in the same way that I did there. So this I will abbreviate as G plus beta, T, X, Y. And then I will define, and this is defined as you see that it's exactly the same definition that I had there. And then G minus infinity. So why did I put infinity here? Because I'm assuming that in flat space there is no temperature. So beta is to infinity, T is 0. So I'm making the notation consistent. So the fact that it's a relativistic QFT, so the commutator space-like separation vanishes, means that G plus infinity is equal to G minus, provided T is here, right? So I have exactly that structure, but now without the strips at a finite beta. It's just, I have two poles here, that something will happen, and then I have a G minus here, and a G plus here. In fact, you can look at your favorite correlator of a scalar field with a mass m, and you can see that it satisfies precisely these properties. Using the same trick that I just did, so some complex analysis, you take the contour and then you shrink it. Sometimes it's called Morera's theorem, sometimes it's called Bogolyubov edge of the wedge theorem. Depends on your choice. We're Italians, we call it Morera, of course. And then you can extend this to analytic function G infinity of Z xy, that is G minus for positive imaginary Z is G plus for imaginary Z negative, and it's either or the other, in the sense that they are the same, when imaginary Z is vanishing, but real Z is less than x minus y. Okay, so on that particular interval. And then there are branch cuts. I don't care about what happens after this, right? That's not part of my analytic structure. So it's defined everywhere apart from those two extended lines. In fact, since it's a relativistic theory, this is simply a function not of z, x, and y independently, but it's a function of the distance. That is holomorphic, analytic holomorphic, everywhere except when modulus of z squared is equal to x minus y. These are the two poles that I have here. Okay, so now, rather than looking at this is flat space. This is just a mass scalar in flat space. Now let's look at what happens to the accelerated observer. I'm a little bit behind. So the accelerated observer follows orbits of the booster BA, right? And we said yesterday that these are hyperbole, vertical oriented hyperbole, and that I can introduce coordinates along the orbit such that I cover the right wedge, and B is adapted. I can define adapted coordinates, so B is cyclic. Then these coordinates are T equals to rho sinh alpha eta, and X equals to rho cosh alpha eta, which guarantees the fact that we have an hyperbola, okay? You can add transverse dimensions. I don't care about the transverse dimensions. I'm just looking at what happens in a plane that I orient with the generator of the boosts, okay? In Rinder coordinates, let me see what I can skip. In Rindler coordinates, the same function as plus, suppose I have transverse coordinates. Sorry, this is flat, this is what I really see, but expressed in Rindler coordinates. Now, what I have to do is show precisely what I was saying earlier. That is that this function, the resulting function, so the function that will be measured by the accelerated observer, is analytic everywhere, but on this structure. It is periodic with an imaginary period, and it is unique. So in order to show uniqueness, I will use the fact that this is the Green's function of the Euclideanized problem, of the Vic-rotated problem on the real, problem meaning the Klein-Gordon on the real line, which becomes elliptic. Okay? So, first thing, extension to the complex plane. I define zeta, which is eta plus I eta E. Then this function has poles when the entire thing vanishes, because that was the property of this f, but the f is still the same, it's just that it will be at a different point. So it has poles where cosh alpha zeta.
This gives you this one, but just on the right place, right? This slope, the whole space.
Yes, that's right. Yeah, because I'm only considering the coordinates on the right wedge. So it's holomorphic apart from these two poles. And then the periodicity follows trivially from the fact that it depends on eta, which is my extension, only via cosh. Right? So it's periodic. With period 2 pi divided by alpha I. So beta is 2 pi divided by alpha in that sense. In order to show that it's unique, so that it's all that is defined by being the Green's function of the Klein-Gordon, of the Euclideanized Klein-Gordon operator, I observe the fact that on the Euclideanization, so after Vic rotation, which formally means restricting to Z pure imaginary, so I'm restricting to eta E, then those functions, this change of variables, is just the change of variables on polar coordinates. So the Klein-Gordon becomes the Klein-Gordon on the Euclidean Cartesian coordinates, because it's just Euclidean polar, you take to polar, and then you take back to Cartesian. So it's unique. Let me repeat it, because I know that I didn't say it, that I said it too fast. So this function is defined by the property that it's solved, that is a correlator of the theory. But we know that the correlator of the theory has the property of being the Green's function of the Euclideanized operator in Cartesian, in flat space, right? This is the Vic rotation. It's the fact that you take the Feynman propagator, you Vic rotate it. In Rindler coordinates, it looks like it's a weird operator with some function, it's some weird function of cosh alpha eta. But if I look only on the imaginary line, then you'll notice that this change of coordinates is simply rho sin, rho cos is just a polar change of coordinate. So it's a change of coordinate that we know just maps Euclidean to Euclidean, plane to plane. So it's again the Green's function on the plane. So, by the KMS condition, so that is the fact that if I find a function that has these properties, then the state that this function is defining via the algebraic approach of quantum field theory is a thermal state. With a temperature T naught that is alpha divided by 2 pi. This I did for the massless scalar, but Bisognano and Wickman showed that this actually applies to all an interacting QFT. There is another subtlety which will become very important with the Hawking effect, which is the fact that this is not really the temperature that the thermal observer is measuring. Because the actual temperature is measured, because the observer follows a word line where the for velocity is normalized. But the measure of the frequency is done with the unrenormalized vector. So there is a difference between the Planck spectrum defined by BA and the word line velocity itself. And the end result is that the Unruh temperature, so the temperature that is measured by an observer, is actually rho to the -1, where this fact, so the relation between TU and T0, so the thing that I just said very quickly, is also called the Tolman's law. It says, this is just, you can just look at the Planck spectrum, measure the frequency, and you'll see that it changes by a factor that is precisely the norm of the time-lag killing vector. So the temperature measured by observer along time-like killing vector Ka satisfies minus k squared T observed. Well, T naught is a constant. T naught is that T naught. But this as an interesting result, as an interesting observation that you can make about the Unruh temperature, which is the fact that as rho goes to infinity, which means that you're going very, very far, rho is the measure of the opening of the hyperbola, is the measure of the intersection. So as rho goes to infinity, as you go very far, far away, then the temperature that is measured by the observer goes to 0. This is the same thing that we didn't say it. We said it yesterday for the acceleration, but it's the same object. It's the fact that we are in flat space. There's no such thing as a temperature. It's just an observer-dependent observation. It's just because we are looking at accelerated observers. But if we look at an accelerated observer very far, far away, she will not measure a temperature. The fact that this happens, the fact that an accelerated observer measures a temperature, is a physical representation of what I was saying earlier, of the fact that there is no notion of vacuum and particles. the notion of vacuum and particles is observer dependent. So the accelerator observer constructs a Hilbert space based on a vacuum that is different from the vacuum that is defined by the Minkowski observer that just follows dt. And therefore, they will not agree on what they call particle. If they have two different detectors, the Minkowski observer observes nothing and the accelerator observer measures something. If, however, you look at local observables, so not something global that depends on your entire word line, such as the expectation value of the stress energy tensor, if you look at something like this, then the Minkowski observer will measure 0. But the stress energy tensor of the Rindler observer is related to the one of the Minkowski observer by a tensor transformation that is induced by the diffeomorphism, by this diffeomorphism, by this change of coordinate. But you know that tensor equations, a tensor equation that is equal to 0 is invariant under tensor transformations. So the stress energy tensor measured by the Rindler observer will also be 0. So everything is good in physics, and we are very happy. Okay. Questions about this? Probably you hear about this tomorrow as well, in a more formal way, in the operator algebra course. So what does this have to do with black holes? And here we come to the fun part. Let's consider a general static, spherically symmetric space. With this particular form. You'll recognize the Minkowski space as this form, but also Schwarzschild, Minkowski, it's trivially this form, Schwarzschild has this form, also ADS has this form, and Schwarzschild ADS, which will be the main character of Thursday's lecture, have the same form. Now, there is a killing vector for this space, which is K GTA. So now it will look very much like the Schwarzschild analysis. It's just that I will be a little bit more general than the Schwarzschild analysis. So there's a killing vector, but the observers that follow the orbits of this killing vector are accelerated because so they are not on geodesics, because k squared is equal to minus f of r, which generically is not a constant. I assume there exists r plus, positive, whatever, such that f of r plus vanishes, and f of r is positive for r larger than r plus. This is the same property that is satisfied by Schwarzschild, but is also satisfied by ADS and ADS Schwarzschild. So I'll do the analysis once with an arbitrary function so that it all follows in the same way. At r plus, k vanishes, the length of k vanishes, and you can show, just by doing manipulations here, that the same manipulation that we were doing yesterday is a killing horizon for k. And moreover, you can also compute the surface gravity, which is f prime of r plus divided by 2. This just followed by doing the same, exactly the same properties that we were studying yesterday. now we would like to study the analogous problem as the Rindler observer, because it's a Killing horizon, and we saw yesterday that Killing horizons all behave in the same way. In fact, well, okay. So we look very close to the horizon. So we introduce a geodesic coordinate such that the line element near near R plus, so the leading order here, is simply minus F prime R plus. Sorry, rho squared. Rho squared. Plus R plus squared. So here I'm going near the horizon of the black hole, or near the Killing horizon defined here. Rindler space satisfies the same properties. I didn't write the metric in Rindler coordinates, but it's precisely this with an alpha. Okay, now I do exactly what I was doing here. So I Euclideanize, because that's what I was doing in order to show the KMS condition. So I define T is equal to ITE. And now, in Euclidean, I know that, as we were saying yesterday, as we were saying just a second ago, sorry, we need to identify TE with TE plus beta. So how do I find the right beta? I will do a sleigh of n. So I will tell you that beta is defined by requiring the space to be smooth. Why there is a smoothness problem? Let's look at a constant rho orbit. Okay? So a constant rho orbit, since TE is identified periodically, is just a circle. Now, in flat R2, circles are defined by in a very formal way, by the fact that their circumference over their radius is equal to 2 pi. It's just a trivial property of circles. But we take this to be the defining property of circles. This is what circles do. On this space instead, circumference over radius instead has beta f prime over r plus divided by 2 times 2 pi rho over rho star. So they have this property. Beta alpha. That's correct. No. Yes, that's correct. And in order for the space to behave precisely like R2, I need this to be equal to 2 pi. Otherwise, the space doesn't close smoothly. And in fact, you have a cone. You have something like a cone. So you know that a cone is locally R2. I take a piece of paper, and you just identify the ends, so it's locally R2, it's locally flat, but overall it's not flat. There is a conical singularity, there is an at the apex, which is a deficit angle. Is a problem with the fact that you have an identification that is not equal to pi. So beta is 4 pi divided by f prime r plus. Why do I impose that this is the which is also equal to 2 pi over kappa? Why do I impose that this is precisely the identification? So why did I do this? At first level, at a very simple, naive level, is because it works for Rindler. For Rindler, I have alpha equal to f prime divided by 4. This is just alpha, that's the definition. And I noticed that beta that I identify there, 2 pi divided by alpha, is exactly 2 pi divided by alpha. So it works for Rindler, and then I say, okay, it works for everything. More formally, you can do a path integral quantization of your theory. So now, in order to do the path integral quantization, you go to Euclidean and you define a path integral by its value on the spatial, by the fact that the path integral over a spatial surface defines a state. And this will become the Arto-Looking state, also called, but whatever, it's a thermal state at a particular temperature. And you assume that they must be smooth, because in the path integral, I'm only summing over smooth configurations. We will see this tomorrow, on Thursday too. But at the first level, it works for Rindler space, and it also works for Schwarzschild space, and that's okay for us. So in this way, we have related geometry to thermal temperature of the black holes. And I've also said, and the result here is that black holes are associated to a temperature that is kappa divided by 2 pi, which is precisely the temperature that I claimed at the beginning. So, have I showed the Hawking effect? No, because I've only spoken about bifurcate killing horizons, which is not what you see in a real black hole. A real black hole is defined by a gravitational collapse. So a black hole has some matter. This is the collapsing matter. This is a spherically symmetric collapse. So, this is the Penrose diagram, is the conformal compactification of a spherically symmetric collapse. In the sense that each point on this diagram is an S2, and I've taken far away at a finite distance. This is far away at far in time. So this is where the stationary observers will be. This is far in the past. And you'll see that far in the past, there is my star that is spherically symmetric, and it does its life. And then at some point, it will become a black hole. So there will be the creation of an event horizon. And here, really, I don't know what happens, but imagine that it works like this. And then classically, at least this is the classical picture, then there will be the creation of a singularity at r is equal to 0, say. Because of Birkhoff's theorem, which is the uniqueness theorem for spherically symmetric space, everywhere on the yellow part of the spacetime, the metric is just Schwarzschild, because that's the only metric that is spherically symmetric and static and has a black hole. Inside here, the metric is not stationary, so there is not even a global time-like killing vector, let alone it being hypersurface orthogonal, so it's static. There's just something happening. So the proper computation to do, if you want to show the Hawking effect, is to take the take an observer here, very far at much later retarded time, and an observer in the past, so just like the Minkowski observer and the Rindler observer. Both of them will be able to define a positive frequency basis and define a Hilbert space and a concept of vacuum and particles, because both of them live in the Schwarzschild geometry, right? Where everything works very well. I have a global time-like Killing vector that I use to define my Hilbert space. However, if observer in the past launches some, or any observer in the past, for the matter of fact, launches some information to the future, some of it, suppose I have an observer here, will be scattered, some of it will just end in the black hole, some of it will be scattered by the Schwarzschild geometry outside and will reach this observer. But there are also messages from the past that in order to reach this observer have to propagate in the non-stationary geometry inside the collapsing matter. This is basically the star itself, right? So what happens is that the observer here measures this part, and it's fine, it works, and there is no Planckian spectrum for this particular type of wave packets that arrive from these points. But the wave packets launched from this point do display a Planckian spectrum that has precisely this temperature, kappa divided by 2 pi. The difference with the Rindler space is that since the black hole absorbs as well as emitting, there is also a balancing factor, which is called the gray body factor. So it's not a pure Planckian spectrum, but it is fine graining point. Okay, so last thing to say about the Hawking effect is the observation of the application of the Tolman's law to the Hawking effect. Sorry, here I just rewrote the Tolman's law, but you'll notice that the difference with the Rindler observer, this is something that I mentioned also yesterday, is that in the Schwarzschild geometry, say, the norm here in the far future, or in the far in spatial direction, doesn't go to 0 or diverge like the norm of the boosts, but it goes to well, the length goes to 1 and the norm goes to -1 and the norm goes to 1. So the constant in the Tolman's law is really the Hawking temperature that you measure at infinity, whereas all the other observers inside that are not very far will measure something that is modulated by the norm of the Killing vector at that point. Okay, but this is the difference with the Rindler, because Rindler at infinity went just to 0, the observable geometry. So it's a real physical effect. Okay, I went very fast. I'm sorry. I went too slow at the beginning. So let me tell you, can I conclude 2 minutes? Okay, let me tell you a few observations on what happens now. Something that we will not do any of what I'm gonna say now, but they're interesting points. So first, we should ask ourselves, what is the physical picture of the Hawking effect? And Hawking himself presents this physical picture in the original paper. The reason the Hawking effect exists is because of a combination, of an awesome combination of the quantum effects and the gravitational presence of the horizon. You know that there is a non-perturbative effects of QED that says that if you take because of the quantum fluctuations. So because at each point in time, the vacuum is not really empty. There is always a creation of virtual photons, say if you are in, or electrons or something, whatever field you want to quantize. If you impose a current, if you take an electric field that is sufficiently strong to pull away these virtual particles and make, they will actually become real, and you can measure a current between 2 points. This is called the Schwinger effect. It's perhaps the only non-perturbative effect in quantum field theory. It was definitely the only known in 1951 when this was published. But suppose that now something like this happens in the vicinity of the black hole horizon. There will be the creation of a pair of virtual quanta, but now on average, one will be absorbed by the black hole, and the other one will reach the observer at infinity. But at that point, from virtual has become real. The presence of the horizon has made it real. So it's really an amazing combination of, this is very intuitive and, and wavy, but it's an awesome combination of the presence of quantum fluctuations of the vacuum and the presence of a classical horizon. There are three other points that I wanted to mention. The first, if a black hole is really a thermal object, then I should also be able to explain or justify its entropy from a microscopic theory. So if I have an entropy that scales like area over 4, then I should be able to count a number of microstates that grows like the exponential of A divided by 4. As far as I know, the only theory of quantum gravity that is able to reproduce this is a computation in various computations in string theory. But this, in some sense, has been done. No computation exists for the real thermal entropy. The computations that have been done until now are non-thermal entropies. They are just the degeneracy of the vacua, because they apply only to supersymmetric black holes that have 0 temperatures. If you believe that the entropy of a black hole is also proportional to the area of the horizon, and if you believe that black holes do form, then there will be a bound on the amount of entropy that can exist in an area, in a volume, that is actually proportional to the area. So the entropy or the degrees of freedom in a volume bounded by area A is bounded by area over 4. Because if I have a too large a number of degrees of freedom, then the gravitational attraction between them will create a black hole. But the black hole, the entropy of a black hole is just proportional to the area. The scaling of the degrees of freedom in gravity, therefore, is not proportional to the volume. It's not extensive in the volume, but it's proportional to the area of the bounding surface. This idea suggests that gravity is holographic, in the sense that the degrees of freedom in gravity are actually measured only by the area surrounding it, so in one dimension less. This is born into reality by another construction in string theory that is called ADS-CFT correspondence, that we will mention tomorrow as well, Thursday as well. Okay, finally, and then I'm really done, thank you. There is a big problem with what I said until now, which is related to the back reaction that I was mentioning earlier. If you also include the back reaction, then the black hole will shrink because it will lose part of its information in radiation away to infinity. But that means that eventually the black hole will shrink to zero size. But that means that if I start with matter in a pure state, so if I take the gravitational collapse with matter in a pure state, it will eventually, then it will form a black hole, then the black hole will disappear at sufficiently late time because it will evaporate, and then I'm left just with thermal radiation. But thermal radiation is in a mixed state. It's not in a pure state, as I said earlier there. So you have an evolution between a pure state and a mixed state, but this contradicts unitarity of the postulates of unitarity. So it looks like a theory of quantum gravity is non-unitary. Turns out that that's not true. Quantum gravity is unitary. And one of the ways you can justify this is via ADS CFT, in the sense that quantum gravity in ADS is perfectly described by a CFT on its boundary, which is a unitary quantum field theory. Thank you. Sorry, I went a little bit over time. Thanks. No, I don't know. I'm just, well, I take it in the sense that that's what I do, but I have to sell what I do. Ah, okay, that's good. I didn't know. Okay. Ah, they proved that it's proportional to the area? Okay, okay.
So, questions, comments, more questions, more comments. But in any case, we have like a coffee break right now, so we can, anyone has more specific questions, we can discuss. Thank you very much.
Thank you.